Select the molecule that best correlates with the following proton NMR spectrum. So in this case, we don't have a molecular formula, but we've got some molecules that are different enough that we should be able to differentiate these. So the key pieces of information that we're looking at from a proton NMR is the number of signals. And I would say it's worth checking the number of signals first here to see if it correlates with what we would expect to see in each of these NMR spectra. So here we see we have 1, 2, 3 signals. It's very possible that only one of these molecules would give us 3 signals in the proton NMR, and then we would pretty much be done. So let's take a look at A. So we have 1, that's another set of hydrogens, 2, 3, and 4. So we would expect this molecule would show 4 signals in the proton NMR. If we look at B, we would expect to see 1. These 2 would be the same. These 2 would be the same. And finally, this last proton would be distinct. So we would expect to see 4 signals. It is possible that these might overlap. If they're similar enough, if they appear in the same region, they might just lay on top of each other. And that sometimes happens in the aromatic ring. They might overlap. So this might look like 3 signals. So in that case, we look to the next piece of information, which is the chemical shift. And these hydrogens of an aldehyde are pretty distinct in their chemical shift at around 9 to 10 ppm, and we don't see that. So we see no aldehyde. And your benzene ring signals is usually between like 6.5 and 8 is roughly the aromatic region, and we don't see that either. So we're gonna say we don't have any aromatic hydrogens either, so we don't have B. For that matter, we don't have A. 4 signals doesn't match, and we're missing the key carboxylic acid signal that would be down around 10 to 13 ppm. So definitely not that one either. If we look at C, we've got a plane of symmetry down the center, which means because we've got these 2 identical ethyl groups, so we would see only 1 and 2 signals. Because this CH2 would be the same as this CH2, this CH3 would be the same as that one. So we would see 2 signals. So it appears that this is a really easy problem to solve just by the number of signals. The only thing we might consider is this one, because it might look like 3, but the chemical shifts don't match at all. So if we look at D, we've got a CH3. That would be 1 signal, a CH2 would be another signal, and then another CH3. So that has 3 signals, and let's just make sure that everything else matches what we would predict. So this signal here would integrate for 3 hydrogens. It would be a singlet because the carbon next door has no hydrogens. And being adjacent to a carbonyl, I'm going to expect that that CH3 adjacent to a carbonyl would be about 2.1 ppm, parts per million. And then these 2 hydrogens, so 2 hydrogens, they would be split by the 3 adjacent hydrogens. So that would be 3 plus 1 is 4, so it would be a quartet. And I'm going to guess being attached to oxygen somewhere around 4 parts per million is that general range. And then finally this methyl group, 3 hydrogens, so it would integrate for 3 hydrogens. It would be split by the 2 adjacent hydrogens, so 2 plus 1 is 3, so it would be a triplet. And I would expect this to be somewhere, let's just say less than 1.5 ppm because it's attached to another alkane. And so we can see that this actually matches really, really well with what we see here. So this 2 hydrogen quartet, we'll call this A. That's the signal for these hydrogens. It matches what we described. The next one, B, these 3 hydrogens, a singlet, and around the range for being attached to a carbonyl. So that's B here. And then finally, this last signal, that CH3 triplet, and around where we said it would be. So this is definitely the right answer.